this set of notes, we're going to continue looking at multiple linear regression, and we're going to start out continuing our discussion of categorical independent variables. So we looked at how to create a model with a single categorical independent variable as well as two and an interaction. And what we're going to look at here is just briefly how we could include three or more categorical independent variables. And what you're going to see is it's very similar to what we would have done before, and you could extend this even further. So once you see the pattern from 1 to 2 up to 3, going even further isn't too bad. All right, so recall that we had that fuel performance example for module 7.3. So if you don't remember that example, take a moment, go back and look at it. But it says most ambulances have diesel engines. An engineer wants to model the performance of a diesel engine as a function of type of fuel and engine brand. And now we're going to add the additional variable to account for the injection system, which is either going to be S1 or S2. All right, so first of all, let's recall what our categorical independent variables are and how we code them as dummy variables. All right, so our first independent variable that we had was type of fuel, and remember there were three different types of fuel. So when we set up our dummy variables, since there were three different types of fuel, we are going to set up two dummy variables. And I'm going to use the first fuel type as my base case. So x1 is going to be equal to 1 if we have fuel type 2 or 0 otherwise. And then x2 is going to be equal to 1 if we have fuel type 3 or 0 otherwise. We also had the engine brand, and there were two different brands, so we only needed a single dummy or indicator variable for this categorical variable. So we have 1 if we have brand 2 and 0 otherwise. So again, I'm going to use brand 1 as the base case. And just as a reminder, whatever you use as that base case, or we could call that the reference case, it doesn't really matter which one that you use in terms of when you fit the model or define your variables, but it will make a difference when you go to make your interpretations. So for example, the values that I would get as my estimates for the coefficients of brand, that will change based on whether or not I use brand 1 or brand 2 as the reference case. So for that reason, when you go to interpret those values, which one you use as the base of the reference case is very important. So finally, we have one more categorical independent variable here, which is the injection system, which has two levels. So it will also need a single dummy variable. And again, we're going to use the first one as the base case. All right, so let's look at how we could set up a model using these three categorical independent variables. So we're going to start out by writing our model in terms of the expected value of y. And as always, we're always going to start out with the intercept. Now, the next thing I'm going to do is I'm going to add in all of the main effects. So the main effects are going to be the ones that deal with each of the dummy variables up above. All right, so these again, these are what we call our main effects. Now, the next thing I need to do is I need to add in all of my two-way interactions. So notice, since I have three categorical variables, there are three different types of two-way interactions I can have. I can have brand and fuel interaction, fuel and system interaction, and brand and system interaction. So let's add those in. So the first ones I'm going to look at are the fuel by brand interactions. So notice this is going to deal with the dummy variables x1, x2, and x3. So the first one I'm going to have here is going to be x1, x3. So what this one is looking at is the interaction between fuel type 2 and brand 2. And then the other fuel and brand interaction that I could have would be fuel type 3, which that's dummy variable 2, and brand 2. So notice these are going to be my fuel by brand interactions. Now I could also look at fuel and system interactions. So I'm going to do the same thing, but notice instead of interacting with the dummy variable for brand, I'm now going to interact with the dummy variable for system. So I'm going to have the following. And so again, these are going to give me my fuel by system interaction. And then the other two-way interaction that we could have would be the brand by system interaction. And so that would be the following. And then there's one more interaction that we need to consider, and that would be the three-way interaction between the three different categorical variables. So the three-way would be the following. So we could interact fuel type 2 with brand 2 and system 2, or we could interact fuel type 3 with brand 2 and system 2. And so again, these are all the possible three-way interactions, which are fuel by brand by system. So one thing to keep in mind is that as we increase the number of variables in our model, we increase the number of potential interactions that could occur, and therefore we're drastically increasing the complexity of our model. All right. So down here in the box we have the pattern of the model relating the expected value of y to k qualitative independent variables. So we just looked at 3, but again, you could extend this up to k, and this box explains how you would do that. Up to this point, we've looked at models with quantitative independent variables and categorical independent variables, but we haven't looked at models that have both. So suppose that we want to model the expected value of y using several quantitative and qualitative variables, then we can proceed in the following way. So we start out by writing the model we want to use to describe the quantitative independent variables. Then we introduce the main effects and interaction terms for the categorical. And then we add terms for the interaction between the quantitative and the qualitative variables. And so this is done by interacting each qualitative or categorical variable with every quantitative. So let's look at an example of how we could do this. In Human Resource Management Journal, researchers conducted a study of workplace bullying. Researchers employed multiple regression model to a bullying victim's intention to leave the firm Y as a function of level of bullying and perceived organizational support. We're going to write a first-order model for the expected value of Y as a function of the independent variables that incorporates the interaction. So in order to do this, the first thing we need to do is define our variables. So I'm going to let x1 be the bullying variable. And then notice that organizational support has 3 levels: low, neutral, and high. So we're going to need 2 dummy variables. I'm going to use low as the base case or the reference case. So x2 is going to be equal to 1 for neutral and 0 otherwise. And x3 is going to be equal to 1 for high and 0 otherwise. And again, remember which one you choose as the reference case, it doesn't actually matter, but it matters in the sense when you go to interpret your model. So you can, to start out with, you could choose any of them to be the base case, but that is going to affect the estimates of the coefficients that you get. So when you interpret your estimates, which one you chose to be the base case is important. So let's write out our model. I'm going to start out with writing the expected value of y and adding in my intercept. Next, I need to write a term for any quantitative independent variables I have. So in this case, I only have one, so I'm going to have beta 1 x1. Next, I'm going to introduce the main effects for the categorical independent variable. So our categorical independent variable is represented by x2 and x3, so I'm going to have the following. Next, I'm going to interact my quantitative independent variable with my categorical variable. So I have the following. And for this model, this is all we have. So since this is the most simple model, we don't have that many terms, but let's say we had 2 categorical variables or even 3 and 2 quantitative, we would follow the exact same steps to set up the model. So we're going to refer to that model that we just looked at, and we're going to demonstrate that the model graphs out as 3 non-parallel straight lines, one for each level of perceived organizational support. So just to start out here, so I have it on the screen, I'm just going to write out what that model was again. And now we're going to look at each level of organizational support, and we're going to start out with low. So remember when we had low that x2 was equal to 0, and we had that x3 was equal to 0. Alright, so let's write our model when x2 equals 0 and x3 equals 0. So we have the following. So notice that all of these terms become 0, and so we're just left with the following. So in other words, we're just left with the simple linear regression when we only had x1 as our predictor. Notice this is because we have let low be our base case. So the simple linear regression, when we have x1, that is looking what happens at the base case. All right, now let's look at neutral. So I'm going to do the exact same thing. And I should note up here at the top, notice for the base case that x2 is equal to 1 and x3 is equal to 0. So now this term and this term are equal to 0. We get the following. So I'm going to combine my terms, and notice we get the following. So again, I'm still getting a straight line here. But notice if we look at the slope of the two lines, oops, let me fix that. So here is the slope of the second line, and here is the slope of the first line. So let's now look at high, and we're going to come back to this idea of comparing these slopes. So remember for high, the x2 is equal to 0 and x3 is equal to 1. So we get the following. And so now notice this time that this term and this term are 0. So we get this. So again, I'm going to group my terms. And again, now notice the slope of this line. All right, so why are these slopes important? Why would we want to compare the slopes of these three lines at the three different levels of the categorical variables? Well, look at what happens here. In the base case for low, we just have beta 1. For neutral, we have beta 1 plus beta 4. And for high, we have beta 1 plus beta 5. So in other words, what's really differing between these slopes, or what's changing these slopes, is beta 4 and beta 5. Well, let's go back and look at what beta 4 and beta 5 represent in terms of our model. So notice in terms of our model, beta 4 and beta 5 are the interaction terms. So if these parameters are actually 0, in other words, if beta 4 and beta 5 are equal to 0, and there is no interaction, notice we would end up with 3 parallel lines. So this relates back to this idea of what we talked about, what it really means to have an interaction. And we can see, if we take the math and we actually look at what happens here, we do end up with those parallel lines when there is no interaction. And that when we do have an interaction, what the interaction is doing is it's changing the slope of the lines. All right. Next, we're going to look at what is called a test for comparing nested models. So we often want to determine which model best fits the data. So in this section, we're going to look at what's called a nested model. Two models are nested if one model contains all the terms of the second model and at least one additional terms. So the more complex of the two models is called the complete or the full model, and the simpler is called the reduced or the restricted model. So we've got an example here. So we could have a full model, and notice the full model here has k betas, and then the reduced model is only going to go up to g betas. So the difference between the two, notice what's missing here. We're going to have beta g plus 1 all the way up to beta k. That's what's missing in the reduced model. So what we do for the test is we fit both the models, and what we do is we look at whether or not these additional parameters here, we look at whether or not they are equal to 0. In other words, we're looking at the parameters that are different between the two models. And if they are 0, or we can't prove that they're non-zero, then what that tells us, we don't actually need the more complex model. We can stick with the reduced model. And it ends up, this hypothesis test is called an F-test for comparing nested models. And we have the summary of it here. So take a moment, look over this, and then I'm going to actually show you how to perform this test. So we're going to look at an example here, and this is actually an example that we've seen before. We just have some more information and we actually have some data. So an experiment was conducted to evaluate the performances of a diesel engine run on synthetic coal-derived and petroleum-derived fuel oil. The petroleum-derived oil was a number 2 diesel obtained from Phillips Chemical Company. 2 synthetic fuels were used, a blended and a blended with advanced timing. The brake power and fuel type were varied in test runs, and engine performance was measured. So the following table gives the experimental results for performance measured, mass burning rate per degrees of crank angle. And so we have the following. So notice, if we look in terms of our variables, we have mass burning rate is our response. Our first predictor is going to be brake power, which is a quantitative. And then our second variable is going to be a categorical variable, which is fuel type, which takes takes 3 levels, so has 2 dummy variables to represent it. And so we're going to fit this interaction model that we have up above, and you'll notice this is the same model that we just looked at. So this is an interaction model between a single quantitative variable and a categorical variable, which has 3 levels. All right, so here is a scatter plot, and first thing you should notice here, these lines are not parallel. So visually this suggests that there's probably an interaction present, and we're going to see how to actually test that. All right, so we're going to fit 2 different models. So the first model is going to be this one, and notice this is the model that we have referenced up above. And this is what we're going to call the full model. Now, as we just saw in the previous example, these last 2 terms, these are the interaction terms. And we just talked about that, if beta 4 and beta 5 are equal to 0, then we know that there's not actually any interaction. So we just showed that in the previous example when we looked at the breakdown of those 3 lines. So what we're going to do is we're also going to fit a reduced model. And so the reduced model is just going to be this piece right here without the interaction terms. And so we're going to see that down here. So notice here is that reduced model. All right, so we got 2 separate models here, and we're going to see how we can use this to figure out if there is indeed an interaction. All right, so the first thing we're going to do is perform the model utility test, and this is going to be for that full model. So since this is for the full model, we're going to use the first bit of SAS output to help us out. All right, so as always, remember the first thing you do for any of these hypothesis tests is we need to acknowledge that these tests are only valid if our assumptions are met. For right now, we're just going to assume that they've been met, and then again later on, we're going to see how to actually check those. This is going to be at the 5% significance level. So the first thing we're going to do is we're going to set up our hypotheses. So this is the model utility test for the full model. So we've actually seen model utility tests in the past, and remember that for the model utility test, what we do under the null is we assume that all of the parameters with the exception of the intercept are equal to 0. And really, when performing inference on any regression model, the model utility test is really the very first step, because it just says whether or not your model is actually useful. It doesn't say what parts of your model are useful, it just says the model itself is useful. And so again, we've seen this hypothesis test several times now. Okay, so we're going to go and we're going to look at our SAS output for the full model. Remember, that was this piece right here. And the first thing we need to do for this model utility is we're going to look right here. We're going to look at this overall summary of the model, and we want to find that test statistic and that p-value. So there is our f-value, and there is our p-value. So coming back down here, we have that f was equal to 25.65, and that our p-value is approximately 0. It was very small. Now remember that if you are reporting this in publication, for publications, you almost always, when reporting an F-test statistic, also give the 2 different degrees of freedom. So for this particular one, if you go back up and you look at the SAS output, the first degree of freedom was 5, and the second degree of freedom was 8. All right, so we see our p-value is low, so we know that we can reject that null hypothesis, and we have the following conclusion. At the 5% significance level, the interaction model with brake power and fuel type is statistically useful at predicting mass earning rate. All right, so again, this is just saying that the model is statistically useful, so now we can go and check some individual things about the model. The other thing to keep in mind here, and I've said this before, the way that I am presenting these is more, from a statistical standpoint, this is the exact interpretation. Often in publication, though, this is not how we would word these things, and there is that shift in publication to just directly report what the p-value is and not compare to a significance level at all. All right, so we might next want to conduct a test to see whether brake power and fuel type interact. So let's again go back and look at the comparison of our two models. So notice we have our full model here, and the reduced model, the model without the interaction terms, is in the green box. Now previously we saw how to test if there was an interaction if there was only a single term that dealt with the interaction. And we could go look at that t-test. But notice here, the part of the model that corresponds to the interaction actually involves two different coefficients, both beta 4 and beta 5. So for this reason, we're actually going to use that f-test for comparing nested models. So notice we do have nested models here. We have the full model, and then nested within it is the model without the interaction. So to conduct this test again, we're going to use that nested f-test. And so let's see how we could do this. So again, for any of these tests, we have the same assumptions. So you would always want to check these. And notice if you had checked this for the previous example, you would also have it met here. So now what we're interested in terms of our hypotheses are those coefficients that deal with the interaction. So in other words, we want to see if beta 4 and beta 5 are equal to 0. And the justification of why we're looking at these, again, that goes back to that previous example where we looked at that breakdown of the three different lines. All right, so if we want to perform this test, looking at that box for the nested f-test, we need the following, and we're going to look at what each of these are. We need the sum squared error for the reduced minus the sum squared error for the complete or full model, divided by k minus g, divided by the mean squared error for the complete. And so this is the formula. We can also make SAS perform this test for us, and I'll show you that later on. But for right now, we're going to look at how to look at the output from the two individual models to see where we could find these values. All right, so we're going to start out by finding the SSE for the reduced and the SSE for the complete. So let's go back up to our output. So here we have the complete model. So if we want the SSE for the complete, notice here we've got sum squares, that's the SS, and so the sum squared error, there's your E, for the complete is going to be this piece right here. And you can also go ahead and find the MSE for the complete. Notice MS is mean squared. And then again with error. So if we find where those meet up, you get this piece right here. And this is your MSE for the complete. And then we need the SSE for the reduced. So we go to the output for the reduced model and we do the same thing. Notice you've got sum squared, error. So right here, you have the SSE for the reduced. All right, so now that we have those values, we can plug those in, and we get the following. Now I'm only going to take these to 1 decimal point just for illustration, but obviously if you were calculating these, in real life and you really needed these values, you would use more than 1 decimal place. Now the last thing we need is that k minus g, but remember that k minus g, all that really is the number of parameters that differ between the two models, or you could even think of this as the number of parameters that you have under the null hypothesis. So under the null hypothesis we have 2 parameters, so k minus g is just equal to 2. And this is equal to 8.7882. And then your degrees of freedom, if you go back up, we'll look at our little box that we have that describes this hypothesis test. So here is our box right here. So notice here is that formula that we just used, or actually we used the second version. And so the last thing we need is our 2 degrees of freedom. So notice new 1, or your numerator degrees of freedom, are going to be the k minus g, which is 2. And then your second is going to be n minus k plus 1. So going back down here, our degrees of freedom 1 is going to be equal to 2, and then our degrees of freedom 2 is going to be equal to n minus k plus 1. So to find this, we need both n and we need k plus 1. So let's go back up to our problem statement. Here, if we look at n, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So n is equal to 14. And then k is equal to the number of parameters excluding the intercept in the full model. So notice that k is equal to 5. So going back down, for our second degrees of freedom, we have 14 minus 5 plus 1, which is equal to 8. Now, to find your p-value, notice what we're really looking at here is we've got an F distribution, where this F distribution has 2 and 8 degrees of freedom. And what we're saying is if we have the endpoint 8.7882 here, the p-value is really that area to the right. And we saw, if you remember way back, second week of class, we saw how to find these values under the curve and endpoints using R. So you could use R here, and you would find that that area, which again corresponds to the p-value, is equal to 0.00957. So notice that value is less than our 5% significance level. So we can say at the 1% significance level, we are able to reject the null. In other words, we can conclude that brake power and fuel type interact. And this is going to conclude this set of notes.